Alrighty, guys, welcome in. Sorry, I am sitting here working on grading, and I totally did not notice that the time had gone past 2 o'clock. So sorry for the late link. Sorry for the late start. We're gonna jump in and get moving here today. Last time we talked about the main application for implicit differentiation, which is related rates problems. And the big idea with those was that you have some sort of usually physical situation, but not necessarily, but some situation which through geometry relates two different objects which are changing over time. And you construct an equation that tells you exactly how those two objects are related to one another algebraically, differentiate through that relation with respect to time, and then plug in and solve for whatever the desired rate is, right? Rate of change that you're looking for. I wanted to look at today maybe a couple more exotic related rates problems, things that are a bit different. The ones we did last time were very standard problems, and they're definitely things you'll see in your homework. You'll see them on the test, that sort of thing. But there are some other problems that are definitely related rates things, but not so obvious, not so obviously related to the types of problems we did the other day. And then the other thing we're going to do today is introduce this notion of linear approximation. So let's get to it. Regarding your exams, I am working on them. I had a problem with the iPad that I use to annotate and make little comments on the written work. I've been talking to the Santa Fe ID people, and it's supposed to be fixed. And so far today, as I've been working, it's been working okay. So hopefully I'll be able to get those wrapped up for you here this afternoon. I know you've been waiting patiently. We'll try to get them done as soon as I can. Today we're going to do a little more related rates. And this thing called linear approximation. Okay. So one thing we haven't had an opportunity to do in the related rates land is look at a problem where there's an angle that's evolving over time. I think those are a lot of fun. And then the other thing I wanted to look at there was kind of a pure math thing, where rather than having some physical situation that you have to read into to draw your picture, you've got something going on that is just mathematical in nature, but still is a related rates thing. So let's get started. Imagine an airplane is flying horizontally over a radar station at an altitude of 5,000 feet. And this radar station wants to track that plane. Of course, these days, radar is a little bit more sophisticated than this, but the radar station wants to track this plane by pointing its dish at the plane. So if the plane is flying over the radar station, the radar station is going to have to rotate that dish to track the plane. Or if you want to pretend like this is a less friendly environment, maybe these are missiles, right? But we want to know how the angle is changing. So we can ask, how fast must the dish rotate? And we'll say in radians per, let's say, second. At the moment the plane is overhead if the ground speed of the plane is, let's say, 250 miles per hour. So this problem has a few things baked into it that the problems we looked at before did not. There is a certain amount of unit conversion because I've got distances here given in feet and then also in miles. I've got time discussed here in seconds and showing up here in hours. So we're going to need to convert all of those distances into 1 unit and all of those times into 1 unit. It's up to us what we want to do. The other thing, of course, is that the geometry is different here. Rather than looking at like some length that's changing over time or something that's falling over time, I'm looking at a rotation. And that means we're going to need to get some trigonometry involved. So first, let's draw ourselves a picture. Here's my radar station. And here's my very crude drawing of an airplane. Okay. So the plane is flying straight ahead, flying horizontally, and it's traveling at 250 miles per hour. That's its ground speed, it's straight speed along the ground. We know that the altitude, since the plane is flying horizontally, the altitude will remain at this 5,000 feet. And the thing that we're trying to track here, if there's a little radar dish on top of this thing that needs to be pointed at the plane, I want to track this angle, call it theta. So as the plane goes overhead, this dish is going to have to rotate and theta is going to change. In order to get started, we need a few things. Like I said, we're going to need to do some unit conversion. But I would begin by drawing this little triangle in here, because this triangle is going to be our buddy. And for the purpose of this problem, we're going to assume that the thing is sitting right on the ground. So I'll say that this is 5,000 feet. This distance, though, the horizontal distance from the plane to the radar station, I need to label that as something. So in our steps where we had to define a variable, this is a variable or a length I'm going to have to define. So is theta, right? We had to define the variable theta to be that angle. So let me call this x. And now we're ready to get started. What I need is some means of connecting the angle theta to this distance x. And I would very much like it to not be more complicated than is necessary. I would like the x, if possible, to be upstairs. And I would like to not have to solve for this hypotenuse. So we know that the tangent of theta is the opposite over the adjacent. We could begin with either tangent of theta, which would be 5,000 over x, or the cotangent of theta, which would be x over 5,000. Totally up to us. Being mindful that we're going to have to differentiate through one of these implicitly with respect to time, I would actually prefer to use the second one, because then the x is upstairs, and I can think of this as 1/5000 times x, which is easier than this where the x is downstairs. You can think of this as 5000 times x to the -1. Whose derivative isn't quite as nice as 1/5000 times x to the +1. Right? I would rather differentiate the bottom. The other thing we need to do, like I said, is unit conversions. So this 5000 is in feet, and this speed is given in miles per hour. We want the rate of rotation, which is going to be d theta dt, in radians per second. So I need to convert this speed into feet per second. That would be my game. That way I can just mess with one thing and get all the units agreeing with each other. So I'm going to say we will use this guy. And then we're also going to do some unit conversion. I'll write down our things we know and things we want. So we know that the plane is going 250 miles an hour in this way. It's up to me to say the positive direction for x, but if I'm thinking of it as this distance, then I would say that that distance is shrinking at 250 miles per hour. So that would mean that dx dt is negative 250 miles per hour. And I'm going to convert that miles per hour into feet per second. It's going to be quite large. So 250 miles per hour. We know that there are 5,280 feet in 1 mile. So this is 250 times 5,280 feet per hour, which is certainly a large number. Instead of crunching that as is, though, let's also get the hours into seconds. Right? I know that 1 hour has 60 minutes, and that each minute has 60 seconds. So I can say that this is 250 times 5,280 feet divided by 60 minutes. And then if I want to go down to seconds, I need to divide by 60 again. So this would be 250 times 5,280 divided by 60 squared feet per second. And that's the SI unit here. So seconds per time. So this is the nice one. That does mean we've got some arithmetic to do, and y'all know I am not an arithmetic expert. I bet I can get to Desmos before Wabbit boots up. Let's see which one goes first. 250 times 5,280. And I want to divide this by 60 squared. So you get 366.67. We're going about 367 feet per second. The thing I want is d theta dt. At the moment when x is equal to 0. Right? At the moment when the plane is straight overhead, I want to know how fast is the dish rotating, which is how fast is that angle theta changing. And you can call that the moment when x is 0. That would be an accurate statement. At that moment, theta is also pi over 2, right? Because theta would be 90 degrees, pi over 2. So now we have everything we need. We've got my relationship between x and theta. I know what I've got and I know what I'm after. I can convert this dx dt into feet per second. Let me go ahead and write that here. This is going to be negative 366.67 feet per second. And now we're ready to go. To avoid further cluttering, if there's any harm in covering up the unit conversion there, I'm going to begin with the statement that the cotangent of theta is 1 over 5,000 times x. And I'm going to apply d dt to both sides. Remember, this is implicit differentiation, so both the theta and the x get treated the same way y gets treated back in section 3.6. The derivative of cotangent is negative cosecant squared. Leaving the inside alone, we get negative cosecant squared theta. And then we need to multiply by the derivative of the inside, which would be d theta dt, or if you prefer that other physics notation, theta dot would be okay. On the right-hand side, the 1 over 5,000, that's a constant. So he can pop out. And the derivative ddt of x is just dx dt. So this is my differential equation into which I will plug all of the things I need and know. It may be convenient to rewrite the cosecant squared stuff, so I'm solving for d theta dt. You know that cosecant is 1 over sine. So this is 1 over sine squared theta d theta dt equals 1 over 5,000 times. And we know that dx dt, the horizontal speed of the plane, it's always that negative 250 miles an hour, which we're going to plug in as negative 366.67 feet per second, because we want to make sure we're using the same units throughout. Negative 366.67, and I'll leave the units off here. I can multiply both sides by negative sine squared theta and get d theta dt is equal to 366.67 over 5,000. The negative will clear up the negative there, and then we just have sine squared theta. And we said at the moment in question, at the moment when the thing is right over top, that's when x is equal to 0. Okay, well, I don't have any x's left over in this expression to plug in for. But at that moment, also, theta was pi over 2, right? The angle the satellite dish is making with the ground is 90 degrees, just straight up. So at the moment in question, theta is pi over 2. So we get d theta dt equals 366.67 over 5,000 times sine squared of pi over 2. And the sine of pi over 2 is 1. So sine squared of pi over 2 is 1. So really our answer is just this guy. And we can approximate that. It's about 0.073. And this
Could you go back and show us how you got pi over 2 for the angle again?
Sure. Yeah, just for cohesion, let me hold here for a second. We can make sure everybody had a chance to write this stuff down, and I'll go back and explain where the pi over 2 came from. So before we do that, any questions on the work done here?
Actually, I have a question on, this is going to be probably basic, but the cosecant squared, why did you convert it to 1 over sine squared?
Oh, just to make it easier to see how to clean this up. But cosecant is 1 over sine, so cosecant squared is 1 over sine squared. I was trying to ask, because I know I'm going to have to plug in some value for theta, and I suspect more of us know what the sine of pi over 2 is than the cosecant of pi over 2. So just because we have greater familiarity with the sine function, I rewrote it that way. That's all.
Okay, thank you.
Mm-hmm. Yeah, if we wanted to, we could have this all just divided by cosecant squared too. That would be just as fun. Any other questions on these steps? The differentiation, any of that? Algebra stuff? So then returning back to answer that first question, how do we know to plug in pi over 2 for theta? Well, we wanted to know the rate of rotation for this dish at the moment when the plane is directly overhead. And when the plane is directly over that thing, picture this triangle evolving as the plane goes by, right? It's gonna rotate like this to track the plane. At the moment when the plane is straight overhead, we're looking straight up. So that angle theta, the angle between the horizontal and the direction the dish is pointing, would be 90 degrees or pi over 2 radians.
Thank you. Also, couldn't you, instead of converting the miles per hour into feet per second, couldn't you just convert the 5,000 into miles per hour?
You could convert the 5,000 feet into miles. That would be just fine. And 5,000 is pretty close to 1 mile. But you still need to convert the hours into seconds because we're asking for the rotation rate in radians per second.
Okay.
So because the units for the answer for d theta dt had to have the units of time downstairs, we needed to make sure that the dx dt had the same units of time downstairs. Yeah, these are all great questions. Oh. Anything else about this one before we move on? Okay. The other problem I wanted to look at, and there's something similar to this in your homework, although not exactly this. I'm going to pull it up in the textbook because these can get quite hairy if you just make up the bits. But you can imagine a particle that's kind of stuck to a curve, moving along a curve. Yeah, I think there's 2 in there, and the one I gave you is not this one exactly, but is quite similar. I don't want to do the exact one. Okay, yeah, we can do this one. Don't state it like that. Interesting. That's okay. I'm not going to do that. So let me phrase this slightly differently. Particle is moving left to right along the curve y equals the square root of 2x plus 1 with horizontal speed (3 units per second. I'd like to find how fast the particle is going up as it passes through the point 0, 1. And there are some variations on this problem, but this is not a strange one. The square root of 2x plus 1, if you want to think about this graph, y equals 2x plus 1, or square root of 2x plus 1, you can graph this by hand by force factoring a 2 inside, and that becomes x plus 1/2. So this is the square root function, but it's been played with a little bit. The x plus 1/2 in here tells you that the graph it's the square root graph, but it's been shifted to the left by 1/2 units. And the square root of 2 out front tells you it's been stretched vertically by a factor of √2. So what I'm going to do is come over here, label this as -1/2, and then draw my kind of typical square root function shape. That top half of a sideways parabola. When you plug 0 in for x, you do get 1 out for y. So this point right here is 0, 1. And the idea is that this particle, you can think of it like this is a track, right? And that particle is stuck along this track. And it's moving along that track, such that the horizontal speed is constant. So the horizontal speed is constant, but the vertical speed is not going to be constant, right? Because this thing's clearly it's going over more than up here. Here it's going up more than over. So over in this part of on this part of the track, in order to maintain that constant horizontal speed of 3 units per second, it's going to be going up very quickly at first. But then as this track sort of levels off, maintaining that speed of 3 units per second, it's not going to be going up much at all. Its vertical speed would be quite low. The trick, of course, is to identify what you know and what you want. So if I label this point as x, y, here's x, here's y, then the fact that the particle is moving at a constant speed of 3 units per second to the right tells me that dx dt is equal to 3. And the thing I want is the vertical speed, dy dt, at the moment when x is 0 and y is 1, because that's this point right here, 0, 1.
How did you get XY Is it just a random point where it would make a,
Yeah, I'm just
rectangle?
choosing to label the point where the particle is at any moment as x comma y.
okay,
If you wanted to use different letters, you could. All right, we could call that A comma B or something else if we want to, but I think it's just nicer to use those because that's what we're comfortable with. So we've got our picture, we've defined our variables, we're aware what we know and what we want in terms of derivatives of those variables. And we were given the algebra relation. There's nothing, we don't need to do anything to come up with the algebra relation. It's right here. So it's just a matter of applying the differential operator ddt to both sides. Of this relation and seeing what we get. ddt of y is just dy dt. On the right-hand side, we may want to remember this is 2x plus 1 all raised to the 1/2 power that we are differentiating. So it's going to give us 1/2 times 2x plus 1 to the 1/2 minus 1 is negative 1/2 times the derivative of the inside. And remember, we're taking the derivative with respect to t. So that's going to be ddt of 2x plus 1. The 1 will differentiate to 0, and 2x will differentiate to 2 dx dt. I just got a scam likely call, but then they immediately called back when I hung up. So let me just make sure that this is bullshit. I'm hanging upside down, naked over a vat of boiling acid. Help, there are alligators. Oh my God, they're biting me. They're biting me. All right. So we differentiate on both sides with respect to time. All we got to do now is plug in the stuff we know. I'm after dy dt, so it's convenient. This is kind of already solved for dy dt. The 1/2 and the 2 on the right-hand side, since everybody here is being multiplied, these are going to cancel. So at the moment, when the particle passes through 0, 1, x is equal to 0, y, if there were any, but there aren't, is equal to 1. And the other thing we know, dx dt, that's always 3. So this will tell us that dy dt is 2 times 0 plus 1 to the negative 1/2 times dx dt, for which I will plug in 3. This is 1 over the square root of 2 times 0 plus 1. And 2 times 0 plus 1 is 1. So this is 1 over the square root of 1, which is 1. All right, this is 1 over the square root of 2 times 0 plus 1 times 3. But that apparatus is 1. This is 1 over the square root of 1 times 3. Square root of 1 is 1, so that's 1 times 3. So the whole thing is 3. I did not set this up like this. Total coincidence that the x and y velocities are the same at this moment.
Can you repeat the part where you plugged in 0 and 3?
So I'm plugging in 0 for x, right? Because this point that we're talking about, 0, 1, that's the x value at that point. 1 is the y value at that point. So if there were any y's left floating around in this expression, I would have plugged in 1 for them. And I'm plugging in 0 for x because I want to know what's going on as the particle goes to the point 0, 1. And at that point, x is 0 and y is 1. And then this 3, that's dx dt. Dx dt is always 3. They told us that the particle is moving horizontally at 3 units per second. So in here, I'm going to plug 0 for x because I'm interested in the moment when the particle goes through this point, and at that point, x is 0. And here for dx dt, I'm going to plug in 3 because that was the value of that derivative that we were able to deduce from the word problem.
You probably explained this on Monday. Well, you definitely did, but can you explain why dx dt didn't cancel out when we got rid of the 2, or we differentiated the
Oh, yeah,
inside the 2x?
And this is one of the things I'm glad you said this, because one of the things I was going to say when I went through this the first time is that we're used to taking derivatives of stuff like this, right? We do it so much that we get in our brain an idea or a feeling for it, and it can be easy to get into that runaway intuition thing. If I was differentiating with respect to x, if I applied the operator ddx to both sides, then this would be 1. This would just be the normal like derivative of 2x plus 1, which would be 2. But I'm not differentiating with respect to x. I'm trying to ask, how is this situation evolving over time? So t here represents time, and I'm differentiating on both sides with respect to the variable t. So this is implicit differentiation. And when we differentiate on both sides with respect to t, since t is not this variable or this variable, we're assuming that x and y are both secretly functions of time. So the baked in assumption here, and this is true in all related rates problems, that x is secretly like f of t, and y is secretly like g of t. So the d dt derivative of 2x plus 1 is like the d dt derivative of 2 times f of t plus 1 all to the 1/2. And then there's a chain rule thing to do here, right? So that 1/2 power comes down, and I have 2 times f of t plus 1 times the derivative of 2f of t plus 1. And that's 1, oh, sorry, I left off the negative 1/2 here from the power rule. So that's 1/2 times 2f of t plus 1 to the negative 1/2 power. And then when you take the time derivative here, when you take this is now like a normal derivative because I've rewritten x as f of t. This would just be 2f primed of t. But if f of t is x, then f primed of t is dx dt. So it's a sneaky implicit differentiation thing where all the variables are implicit functions of a third variable that we don't even list anywhere in the problem, which is time.
Okay, perfect. Thank you.
Yeah, no problem. It's cool stuff. It's cool stuff. And it always takes a second. These kind of more pure math related rates problems are the places where people forget to differentiate implicitly because we do so much differentiation of stuff like this. And we're so used to thinking of that as just being a 2 here rather than 2 dx dt. And that's exactly why I wanted to do this one. So good catch. All right, I'm going to leave related rates there. We worked some other examples in class on Monday. And there are plenty of more problems for you to work in the homework. This is one of those sections where I would encourage a little bit of stuff beyond what's in the homework. So when I assign the homework, I'm thinking of like the minimal problem set that you can do to get a good feel for the material, but it's certainly not enough to become an expert at it. And if you want to get to a place where you're like really comfy, because I know that these word problems, they just tend to be kind of sticky, I would go into the book and look for a few. There's lots of really clever problems in there that are actually a good deal of fun. The next place we're going is section 310 on linear approximation. And this section technically has like 3 parts. We will only be doing one of them. One of the other parts on differentials, we will come back and address later in the semester when we're getting ready to do something called U substitution, because that requires taking differentials. But the book abuses the notion of a differential quite badly. And I am not okay with that. As someone with a bit of a background in differential geometry, I kind of cringe every time I see them replace dx by a number. So we ain't doing that shit. It's just wrong. It's full of lies, it's dirty, and it's wrong. But linear approximation is not certainly wrong as a topic. It's just the way they approach that particular bit of notation. The big idea here is that near the point of tangency, you imagine a curve and a tangent line at a point. Near the point of tangency, the curve y equals f of x is very close to its tangent line. Very close to its tangent line. This is a place where drawing pictures can be a little challenging without good steady hands, which for whatever reason I don't have today. But let's play it like this. Here is an x value a, and here is that point of tangency, a comma f of a. And if I construct the tangent line to this curve at that point, that would look something like this. If we stay close to this point, the tangent line and the curve are really close to each other. And by that, I mean the vertical distance between the tangent line and the curve is quite small. In fact, you can take this to be the definition of the derivative. You can define the derivative to be the slope of the line that minimizes the vertical distance on an open interval centered at A. So the distance I'm talking about there, if we take some x value here, which is reasonably close to A, and you look at the distance, the vertical distance here, it's quite small. Now, of course, if I wander very far away from the point of tangency, this won't be true anymore, right? Like if I look way over here at 0, that tangent line is going to be up here, and the curve itself is way down here, and that's not a small vertical distance. But if you stay a reasonable distance away from the point of tangency, then the y value on this blue line is very close to the y value on the black curve. And you might ask, why do I give a fuck? Because sometimes getting the y value on the curve is difficult. Think about calculating square roots, right? Trying to calculate the square root of 3.9 or 4.123. Those are not nice numbers. They're nasty, irrational numbers. But you can approximate them reasonably well by plugging 3.9 or 4.123 into the blue function. And because tangent lines are, by definition, linear functions, their graphs are straight lines, there's never any weird algebra involved when you plug into them. You'll never have to raise x to a weird power or take the sine of x or anything strange like that. So it's very, very easy to plug into the blue line. So why do this? Well, f of x, the y value on this curve, right? If this x value I just labeled as x, then the y value there is f of x. F of x might be hard to calculate. You know, involving square roots or trig. You know, you can imagine other stuff. Like, what is the sine of 1.5? I don't know. I don't have a clue, right? But if I call that blue function L, then L of x will always be easy to calculate. Because the tangent line is a linear function. You know what makes linear functions linear? Well, they only ever have x to the 1, and all you ever do is multiply by a constant and maybe add or subtract some numbers. So you'll never have to do any complicated arithmetic operation to plug into a tangent line, but you might have to do some horrendously complicated arithmetic to plug into the function from which you got the tangent line. So with this in mind, I'm going to define something for you. This I've written it here and labeled it here as L, but there's some language that goes along with this. The linearization of a function f at an input, say x equals a, is, and then there's two ways to think of this. I'm going to give you a formula. I'm going to write something down here, but here's how I want you to think of it. It's the tangent line solved for y. It's the tangent line written as a function. Okay, so what is that? Well, L of x equals, tangent line normally is like y minus y1 equals m times x minus x1, where m is f primed of a, x1 is a, and y1 is f of a. So if you solve that for y, you get f primed of a times x minus a plus f of a. And this is called the linearization of f at a. It's also called the first order Taylor approximation for f at a. And you'll hear more about that in Calc 2 when we talk about second order, third order, infinite order approximations. But for now, for us, we should think of it as the tangent line. Just solved for y and written as a function. So if you take the tangent line, solve it for y, and then in place of y, you write L of x, that is your linearization. I don't know what's cracking me up. Okay. I know. So the utility here is things like calculating the sine of 47.2 degrees, right? How the hell are you going to do that? Or calculating the square root of 3.98726. How the hell are you going to do that? This is how your calculator does that. sophisticated calculators would have more terms over here, something involving x minus a squared and the second derivative, perhaps a third order term, but this is the game. So let's do it. Let me see if we can get a nice approximation for what we want to do. Natural log of 2 would be fun, but 2 isn't close enough to any really nice values of e, powers of e. Let's go with a square root to start. Let's approximate the square root of 4.12 using the linearization of f of x equals the square root of x at x equals 4. So I'm going to construct the tangent line to the square root function at x equals 4. That's going to give me a linear function, L. And then into that linear function, I will plug whatever x value I would plug in here to get this. Maybe let me add a little addenda here before we run off. I'm sorry to do this, but the big idea is that if x is reasonably close to a, then L of x will be reasonably close to f of x. That's the idea. So you can plug in whatever you would want to plug into f, but can't because the arithmetic is nasty. You plug that into L instead. The only requirement is that that x value you intend to plug in needs to be somewhere close to the x value where you made the tangent line. There are quantitative versions of this theorem that tell you a little bit about the error. We're not going to worry about that right now. Okay. So I need the tangent line. Which means I need the point and I need the slope. The point is 4 comma f of 4. And since f of x is the square root of x, that's 4 comma 2. That's my point of tangency. The slope is going to be f primed of 4, where f primed of x is the derivative of the square root function, which is 1/2 times x to the negative 1/2, or 1 over 2 square roots of x. So my slope, which is f primed of 4, is 1 over 2 square roots of 4, which is 1 over 2 times 2, which is 1/4. Would you ever have believed in the first week of this class that we'd get tangent lines so quickly and nonchalantly? So the tangent line is y minus 2 equals 1/4 times x minus 4. And I need to solve this for y. I like to leave it in, I don't like to distribute this. And you'll see why in just a second. So don't distribute the 1/4. And in general, when solving these problems, don't distribute the m. Just leave this as 1/4 times x minus 4 plus 2. Because our intent is to plug into this thing an x value that is, one, not very nice, and two, quite close to 4. So being quite close to 4 makes subtracting 4 from you a pleasant operation to do. But if you distribute everything, then it gets a little nastier. All right, this is L of x. L of x is just the tangent line solved for y. Oh, x minus 4 plus 2. Okay. Finally, the square root of 4.12 is exactly equal to f of 4.12, which is approximately L of 4.12, which is exactly 1/4 times 4.12 minus 4 plus 2. And that, see what I mean here by not distributing? Now this is easy. 4.12 minus 4 is 0.12. And 0.12 divided by 4 is 0.03 plus 2. So that's 2.03. So I claim that the square root of 4.12 should be pretty friggin' close to 2.03. Now it's 2022. Do I need this to calculate that square root? No, I just go square root 4.12. Yeah, okay. But 2.02977, that is achingly close to 2.03. We're off by less than 1/1000th. In fact, we're off by less than 3/10,000ths. We are extremely close. This will build you bridges, right? This will build you airplanes. This is almost good enough to get you to the moon. First order linear approximation is sufficiently accurate for everything you need in the Industrial Revolution and about 1/4 of the information era when it comes to engineering precision. It's good stuff, man. It's really good stuff. So if you're ever on a desert island and you need the square root of 4.12, you can now do a little bit better than say, I think it's a bit bigger than 2. You can say, I think it's about 300ths bigger than 2. Quite correct. Other place this really shows up in a useful fashion is with trig functions, right? Evaluating the sine of 30, 34 degrees or whatever is not a thing you can do by hand, or exponentials, like the, about how big is e raised to the pi. That's a little tough to figure out on its own. Or the natural log function, right? If I want to evaluate the natural log function anywhere other than a power of e, then I'm not about to do that by hand. So let me just for fun here, let's see, how big is e squared? It's about 7.3. Let me see, how big is e cubed? 20.085. Okay, so let's I should hold here from questions on this. Questions on what we did here, how we got it, or why we're doing it. All feel pretty good. There is a step sometime in these problems where you need to think more carefully about the x value you're going to plug in. So if I used, instead of f of x equals the square root of x, if I was using f of x equals the square root of 1 plus x, then in order to get the 4.12 under my square root, the x value I would be plugging in is 3.12. And you have a choice in what function you're going to use for your approximation in some problems, right? I think the problems I assigned you, they all specify. But if I just said approximate the square root of 9.4, then you could use the regular square root function and the base point of 9, or you could use any other function that has a square root in it, and whatever x value as your base point would get you that number inside, or get you close to that number inside. And sometimes there are good reasons to do things one way or the other. So we said e squared is in the neighborhood of 7.3, 7.4, something like that. So let's try to approximate the natural log of 7.4. And again, I'll kind of give us everything we need. I'll say use the linearization of f of x equals the natural log of x at x equals e squared to approximate the ln of 7. Right, and the way I chose the number 7 and e squared here is because 7 and e squared are quite close to each other. I was just trying to think of a number that's hard to plug into the natural log that is reasonably close to something that I could easily use as a base point. Does that make sense? So again, this is really a tangent line thing. Nothing more than that. My point is going to be e squared, comma, f of e squared, and the natural log of e squared is 2, so that's e squared, comma, 2. My slope is going to be f primed of e squared. Oh, and we're not going to be able to get rid of those, are we? That's okay. Where f primed of x is the derivative of the natural log function, which is 1 over x. So that m tan is 1 over e squared. E to the negative 2. This isn't going to be as fun as outside. Then the tangent line is y minus y1, which is 2, equals m, e to the negative 2, times x. Oh, wait. No, this won't be too bad. Minus, well, no, it's not going to be as nice as it could be. Means that my linearization of x e to the negative 2 times x minus e to the negative 2 plus 2. So the natural log of 7, which is exactly equal to f of 7, will be approximately L of 7, which is exactly e to the negative 2 times 7. This is an e squared, sorry. 7 minus e squared plus 2. And this isn't going to be as easy to come up with a nice clean decimal by hand because the powers of e don't go away entirely. When we distribute this power of e here, which would not be an unreasonable thing to do because subtracting this is not going to be pretty. When we distribute this guy, we will get e to the negative 2 times 7 plus, or sorry, minus 1, right? E to the negative 2 times e to the 2. I'll write it up for now. Plus 2. And this product is 1. So in other words, this is 7 times e to the negative 2 plus 1. And it is the case here that in order to get a decimal, you would need some way of calculating this power of e. And then you multiply it by 7 and add 1. But you can get a rough feel, right? E to the negative 2 is somewhere in the neighborhood of 1/7. So this is going to be very, very close to 2. 7 e to the negative 2 plus 1. Yeah, 1.947-ish. But definitely the fun versions of these problems are the problems where you're able to get a really good feel for the size of the thing without having to resort to any calculator work. That really is all I had to share with you guys today. So I will go ahead and leave it here. You do have some of these linearization problems in your homework. Down the road, we will talk about this section again when we come back to take differentials. But for now, all I want you to get out of 3.10 is this ability to approximate weird function values by plugging into the tangent line instead, and then trusting that the tangent line isn't going to be too far from the original curve as long as the input you're plugging in is close to the point of tangency, close to the x value at that point of tangency. And there is a lot of fun stuff you can do with this. So I hope you enjoy those homework problems. If you have a hard time with any of it, of course, come by office hours, send me a Canvas message. You know the drill, and I will continue working on your exams and try to get those ready for you as soon as I possibly can. All right, take care.